Yay! Potential energy functions. Yay, potential energy functions. Hey, you will like potential energy functions. Because they don't move.
Hey, they know.
Work equals negative delta U. Okay, everybody. Shh. Here we go. Here we go. Here we go. All right. Work integral F dot dr equals negative change in potential energy. Okay? That's equation number one. Because remember we said that the work done by a conservative force, you want to put that in there, work done by a conservative force is equal to the negative change in its own type of potential energy. So if gravity does positive work, if gravity's doing positive work, what's it doing to an object? Actually, I mean if I have this right here, and if gravity does positive work on it, what's it doing to it physically? It's pulling it down and it's moving down. Okay, so if it moves downward, what happens to the gravitational potential energy? It decreases. So if this is positive, then the potential energy will be negative. So you might want to put the potential energy from that conservative force, okay? So these are connected. This is the potential energy function for that conservative force. This is the conservative force, okay? All right, and this only works if you have conservative forces. If you have some other random force like friction or some other force that is not a conservative force, this is not valid, okay? All right, you can rearrange this also. You can write the conservative force function is equal to the negative du, dr, or ds, or whatever for that conservative force, for the conservative potential energy function. All right, so let's do this. Let's say we're lifting an object. Lift object. Lift. Ta-da! All right, let's figure out the potential energy done for that. Okay? All right, how much force does it take to lift this object?
At least.
Yeah, we're going to assume that it's mg, right? Yeah, we'll assume constant speed. Well, let's say that you lift it from here to here. Okay? So it begins at one speed and ends at the same speed. 0 and 0, right? So it's all going to work out in the end. So like if you accelerate it with a force greater than mg, but then if you bring it to rest, it starts at rest and ends at rest, then somewhere along the line you'll be lifting up with less than mg, so it decelerates.
Gotcha.
I was thinking that work is changing kinetic energy, right? Well,
I know, decelerate. Okay, so it's changing kinetic energy 0, right?
So there's no work.
But it changes potential.
Okay, so the deal is, now remember, okay, good point. We have this, work equals the change in kinetic energy. But this is the work done by all forces. Okay? One, it's the work done by all forces. Okay? So you've got gravitational plus yours, right? Okay, so now we're just looking at work done by the conservative force only. Okay? All right. Because if you lift an object and it starts at 0 and ends at 0 velocity, no change in kinetic energy, no net work done because you've done positive work, gravity's done negative work, and they cancel out. Okay? All right, so this would be mg, right? So I'm going to lift it from 0 to a height of, how about h? From here to here, h. So that's mg dr equals negative Okay, but we're talking about the force done by the work done by the conservative force. Which way is the conservative force?
Down.
Which way is gravity?
Down.
Down. So I got mg dot dr. What does that become?
Negative.
That becomes negative, right? The dot product gives me a negative, right? And so this becomes, negatives go away. That means my gravitational potential energy is mgh. Ta-da! That was easy. Wait for it. Wait for it.
Oh!
Got it? Yeah. Wait, wait, wait. Ah.
I might see it.
Got it?
Wait, why is it positive?
Because the dot product, the gravity force is this way, but you're moving it this way. So the angle in between is 180. So the cosine of 180 is -1. Now I can put all those steps in there if you like, but the negative's going to cancel out, right?
Yes.
Okay, let's do this in general form. What if you have a planet? Planet Earth. Very large person on planet Earth.
Looking balls.
We lift this person from here to here. Okay? To this location. R.
How do we lift them?
How do we lift them? With a rocket pack.
That's launching.
Alright, now I'm interested in the work done by gravity. Okay, we're going to redo this same thing right here. We're going to lift this object. This object has a mass m. The Earth has a mass m. M1 and M2. Okay? Rightio. Oh, but we've got some math issues going on here. This is R1 and this is R2, right? Okay. Ooh, I hope this works out.
And then massive strings tend to be atmosphere. No, then gravity varies.
All right. What is the conservative force in play here?
Changing weight.
But it changes. Yeah, but gravity changes.
What is the conservative force in play? Gravity, right?
It's not.
What is the equation for gravity?
G.
Negative G. And 1 and 2 for ours.
Dot dr. And since this is our conservative force, this is going to be big G. I hope my negatives work out. Half the time when I do this, I end up with a wrong negative sign. So I hope this works out properly. Okay, we're going to be going from R1 to R2. Okay?
Okay.
Okay.
Sounds good.
So that works. Negative G and
Well,
1
that
and
negative
2
G
are
stuff,
constants.
dot, dr, does that just make it...
Okay, negative G. Okay, this dot dr. Which way is the force of gravity?
Down.
Downward. Which way is the work? Which way is the displacement? Up. So our dot product is going to give us a negative, right? See, I hope my negatives work out. Half the time I double account for my negative. So this dot product is going to make a negative itself, which takes that negative away. I hope this works out.
Can't you just pull the G out in front of it?
Yes. In fact, we can pull all this stuff out, and we end up with Gm1, M2. So we get dr over r squared. What does that become?
Negative.
Negative 1 over r.
Something.
Negative
1 over r.
1 over r.
I think your negatives are going to work.
Yeah, the word.
Nope, I had one too many.
Okay.
I had one too many negatives because I'm going to end up with positive and it's supposed to be negative.
Or one too few.
You know what? I did have one too negative. One too many negatives because I put a negative on my equation which showed the direction of it already, and then I did the dot product which double accounted for the direction. Anyway.
That's it. I think that's it.
Oh, sorry,
Wait,
over r.
Can you say it's a
R
negative?
from R2 to R1.
What?
R1.
R2.
Wait, we're letting you.
No, it works out. It works out.
How did you double account for that? Now?
Hang on. All right, does everybody see that our potential energy, gravitational potential energy in general is in this form?
Yeah.
That our gravitational potential energy, we just derived this one. Here we go. This one is mgh. This one is good if little g is not changing. Okay? Like you're inside the atmosphere. Little g is approximately 9.8 the whole time. Okay? That's great. But in general, it's big G, m1, m2 over r. That's really the potential energy. Okay? Not squared. We got rid of the squared. It was squared here, but when we integrate, it goes away.
Yeah, sorry, potentially.
Right? Now, I messed up my negative sign. I double account for my negative. This is supposed to be negative. Okay? Here's where I messed up. The force of gravity is in this direction, and the work is this direction. And so I already accounted for the direction of it, and then I accidentally put in this negative g, m1, m2 over r squared dot dr. I shouldn't have put this in because I already took it into account when I did the dot product. I already took the direction into account. So I double accounted for my negative.
So
Sorry.
should we ever?
So what we end up with is this is that, and we end up with negative then. When I move this to the other side, we end up with a negative. That was my fault, sorry.
Should we ever include a negative sign within the dot product?
If you are, okay, I'm going to say this, and I hope this is always correct. If you draw your picture and you're doing your dot product, and you already have drawn the direction of your force in your diagram to know the direction of it, then you shouldn't put the negative sign down. It's just like same thing with F equals negative kx for a spring force. If you draw it in your diagram, the correct direction, then you've already taken into account that negative already.
Okay.
Okay? All right, so we end up with this form for gravity. Okay? Gravitational potential energy. We already did spring the other day. We got a 1/2 kx squared. Because we did this same thing the other day. All right? And so there you have it. Those are our three major potential energies. There is another one that we will run into, not really this semester, but there's another one, which is electric potential energy.
Okay.
Can we go through spring potential one more time?
You do the spring one again?
Speedy Gonzalez.
Sure. Here, I'll just keep this same green equation up here. All right, so we're doing this for spring. So this becomes spring force dot dr. Actually, let's do dx since it's a spring equals negative delta potential energy for a spring. Okay? All right. What's our spring equation? Actually, let's do this again. Here's our spring. If, doesn't matter how you do this, let's say that you compress the spring. Let's just make it positive so it's easier on us. Okay, let's say this is x equals 0. That's our equilibrium position. Let's say that the spring is moved out to here, or the object's moved out to here. Okay? All right, the displacement is positive. The spring force is, okay, if the displacement of the object is this way, then the spring force is this way, right? Okay, so our spring force is kx. I'm just putting kx because I'm writing the direction right here. Okay? I'm showing my direction in my diagram. All right, so when I do the dot product, what should I end up with?
Just negative kx.
Okay, I should end up with kx dx, but there's a negative sign because my dot product, they're in opposite directions, right? And we're moving it from 0 all the way out to x. All right? You see that my negatives will go away. And I'll end up with 1/2 kx squared equals my spring potential energy. Look right? All right, so there's my spring potential energy. Now we can do this again, and we will do this again when we get to next semester, for electric potential energy. It's the same exact derivation as this one. And since electric force is equal to 1 over 4 pi epsilon naught Q1 Q2 over R squared, when you plug that in here and take the integral of it, you're going to end up with the same form as this one again, right? You're going to end up with 1 over 4 pi epsilon naught Q1 Q2 over R. Okay? Does that make sense?
Yes.
I'm not going to repeat that one because it's the same exact integration. Okay? All right, so there we go. There are others that you can come up with. In fact, here's the really cool thing. Sorry. Here's the really cool thing. If you have a planet here, or a sun here, and you have a big planet here, say it's Jupiter, and say here you got another planet here, say it's Saturn.
All
right.
Because calculate gravitational pull.
So you could calculate a potential energy function all the way throughout here. You could map it all out and make a big map of the potential energy all over this solar system. Okay? Now, look what it's going to look like. Look at the potential energy right here. What does the potential energy look like for just the sun? Okay, if I was going to graph the potential energy and say here's the center of the sun, here's the radius from the sun, what's the potential energy look like?
To the graph.
It's negative. These are all constants. And you got 1 over r squared, right?
1 over R.
I'm sorry, 1 over r. So it's going to look like this, right? So you're going to have, it goes like this, and it goes asymptotically to 0, and it goes asymptotically towards infinity. But it won't go to infinity.
What's that
Where will it go to?
The radius.
Right here, the radius of the sun. So there will be
Or you burn up and you
Yeah.
pass
a minimum potential energy when you hit the surface of the sun. Okay?
And then your ashes are
Hey, by the way, when we get to gravity, we'll figure out what we have inside here. What potential energy looks like inside the sun.
black matter.
Hey, by the way, a black hole, here's the deal about a black hole.
It's a sun with a really small radius.
Yeah, it has a tiny, tiny, tiny radius. It has a huge mass, so not only does the graph move down because it has a bigger mass, it has a tiny radius, technically close to nothing. And so that's why you get this huge, what they call a singularity, where it drops down in. Yeah,
Why would we need to know the potential energy inside
because it's cool.
Science.
So, now, how many of you have been to like a mall or someplace where they've got one of these hyperbolic cones where you take your coin and it rolls in?
Then you catch it right before
Ta-da! All right, a nice hyperbolic cone.
Is that why they say
Yeah.
Is that why they say gravity warps space because it does that?
Yes. And so one of the views of gravity is not that it's a force, but that what it really does is it just warps space. And that light and all things just travel, well, light, just say, travels in a straight path, but that what happens is it travels in a straight path across a curved surface. So it changes direction. Think about it for a second.
Really is Halloween.
Yes, it is Halloween. Now, think about that for a second. How is it possible for you to say walk in a straight line, but for you to change direction?
You walk on it.
If the line is curvy.
Yeah. Just think about walking on the planet. If you get on the equator, and if you have your nice floaty shoes, and you walk all the way around the equator, you're walking in a straight line,
Yeah, it's
in a circle.
have to do a straight line. It's going to end up to be a curve.
Yeah, in fact, like Euclidean geometry is all in a plane, right? But like if you have the Earth, and you have the equator, and let's say you start here, and you walk this way, and then you walk straight north to Santa Claus, and then you turn and you walk straight down like that, you'll have a triangle that has 3 90-degree angles in it.
Yeah.
Wait, I can go away.
Now, let's talk about potential energy functions for a minute. Okay? Let's talk about this gravity one. By the way, you can draw a gravity one then, and what will happen is you'll get, I'm only able to draw a slice through the gravitational function. Okay? Potential energy function. So you'd have something like this here, and then you'd have another one for Jupiter, and you'd have another one over here for Saturn. And think of that as a big 3-dimensional, well, we can't do 3-dimensional, 2-dimensional plane. Think of it like a big trampoline where different people are standing on the trampoline and it bends down to where each one is. That's what this would look like in 2D. In 3D, I have no idea what it would look like. Okay? But that's kind of the idea that Einstein came up with general relativity, is that space is warped. Space itself is warped into these shapes. Anyway, yes. Oh, I'm done. All right, so let's take a look at this potential energy function right here. This with the sun.
Can we go to the science place? That would be a great
Yeah, before it closes.
I got. All right. If you place an object on here, okay. Now we're going to work backwards. If you place an object right here, what will it want to do? Go, go, go. All right, now, everyone, here you go. F, the conservative force, equals negative du dr. Okay, will you please figure out what is the conservative force for this?
Big G.
Okay, you got me there. Big G. You're taking the derivative of this. What does that equal?
There's 3 negative signs.
So it ends up being negative. I was going to say, it's got to be negative. All right.
Why does it make it?
There's 3 negatives involved.
There's 3 negatives.
Where?
You want to explain it?
Yeah. There's a negative out front, negative du dr, right? There's a negative included in the u.
Oh, okay, okay.
And then when you take the derivative of u, you get a negative.
Yes.
One over r.
Oh, wait a minute. Yes, that's where I'm messing up. There's a negative out front.
Okay, see.
That's where I'm messing up. I'm looking at it going, this is going to end up being positive, and that's not right. I forgot my negative. All right, so we have a negative out in front of the derivative itself, and then there's a negative on the equation, and when you take the derivative, you get a negative, and so this negative cancels that negative, leaving it negative. Ta-da!
Are you positive?
All right. All right, now everyone, let's make it easy. Everyone, look. Let's make it easy. On a graph, what is this?
The slope.
Slope. It's the negative slope. Negative of the slope. Got it?
Yes.
What's my slope here?
Positive something.
And so my force right here is going to be negative. The force is equal to the negative slope. My slope is positive, so the force right here is going to be that way. Does everybody get that? Towards the sun. Notice that's what we get here too. The force is towards the sun. Where is the force towards the sun greatest? Wherever the slope is greatest. Is this stable? Will an object ever be at rest and stay at rest in this situation we have right here?
Until it is on the sun's radius.
Yeah, unless it's at infinity, where the slope is 0, so there's no force, so it could stay at infinity. But if you're anywhere close to the sun, you will fall in.
What if you're on the sun?
Yes. If you're on the sun, well then you'll have more than one force, and so...
I think you'll have more than just the force.
Yeah, you'll be crispy critter too. But yeah, you'll at the if you're on the surface of the sun.
But you'll be at rest. Like,
But there is no true surface.
Well, there's no real surface, so you really fall through.
Right.
But there'll be other forces at that time.
I'd be dead way before that.
Yes.
So.
All right, so
But like if it was Earth,
yes,
I'm on the surface of the Earth.
right,
I'd be at rest.
right. Now, hey, I'm losing some of you. Okay, you notice that there's no stability point here. That the object, if it's anywhere between here and infinity, it would fall into the sun. Got it?
Yes.
As a general rule then, if you have a potential energy function that looks like this, where do the objects want to move? Towards lower potential energy. Think about that for a second. Objects naturally want to move towards lower potential energy. If they can, they will. Alright? They want to move to the lowest. They want to give up their potential energy if possible. Okay? Now let's look at a different one. What if we have this? What if we have this type of potential energy? 1/2 kx squared. Will you graph that for me? What does potential energy for a spring look like versus x?
Parabolic.
Parabolic up.
Parabola up. Now, everyone, what if you are located here? Which way is the force on the object?
That way.
How do you tell?
Okay, how do you tell? Because the force, here it is over here, the conservative force is equal to the negative of the derivative, or the negative slope. Which way is the slope? Slope is positive, so the force will be in the negative direction. So the force is this way, causing the spring, or causing the object to move back. What if the object's over here? You have a negative slope. Sorry, I should have put a negative force here. It's to the left. I have a negative slope. So therefore, my force will be in the positive direction. I'll have a positive force pushing it back. Do we have an equilibrium position here?
Yes.
Yes. What's the definition of equilibrium?
Where?
Where all the forces equal 0. How do I know the forces equal 0 here?
Slope equals 0.
Because the slope is 0. Okay, we had a question. Yes. Sydney.
How come it's always like that and it's not like that? Or like your force, how come your force is only in the x kind of thing?
Oh. Because this is an x function. And so my force is only going to be in the x direction. Now if I take the derivative of this, let's find it out. What's the negative derivative of this?
Negative k.
It's negative kx. So if I was to graph that, it's going to look like this. And so when I'm over here at this location, I have a negative force. And when I'm over here at this location, I have a positive force that pushes me back, or pushes the object back. Now, you see this? An equilibrium position. See over here? No equilibrium positions. Okay, now, what if I had a potential energy function that looked like this? Here. There's my potential energy function with X. Is there an equilibrium position?
Yes.
What's different about this equilibrium position from that equilibrium position?
Harder to get to.
You still have potential energy.
True. But there's something a little bit bigger.
Bigger and better.
What if I'm here? Which way is the force on the object? I have a negative slope, which means force to the right. If I'm over here, I have a positive slope, which means force to the left, negative of the slope. So,
It'll only get there if it starts there.
okay, here's an equilibrium position, but is it stable or unstable?
Unstable.
This is an unstable equilibrium position. This is a stable equilibrium position. Now, what's our test for concavity? Second derivative, positive or negative, right?
Yes.
Okay, so to check for stability in your potential energy function, hang on, Andy, I'll be right there. To check for stability, you take the second derivative of your potential energy function and you check to see, is it positive or negative? Okay? If it's positive, now wait a minute, we're talking for concavity here. So first of all, where will we have equilibrium? Where the forces equal 0, right? So you take the first derivative and you set that equal to 0. Every place there will tell you where you have a stability point. You take the second derivative, plug in that same spot, check to see if it's positive or negative. If it's positive, it's concave up, and it'll be a stable position. If it's concave down at that 0 spot, then it will be an unstable equilibrium. Yes?
So, can you have more than one equilibrium? Like if you had a water
Yes.
ride that was like this and then like that.
Exactly. And the nice thing about these is we kind of have a visual representation of this if we just think of roller coasters. If we had a roller coaster that went like this, okay, we have a stability point here and here. Let's get rid of that one. We have a stability point here and here. But that's we have an equilibrium, equilibrium here and here. But this one's stable and this one's not. Is it possible for the roller coaster car to get right here and stop and stay there?
Yeah, it is.
Yeah, but it has to be exactly right there. If it's a little bit one way or the other,
It's gonna start falling.
it's going to start falling, right? Okay.
It couldn't be right there.
So in theory it can be there, but will it really be there? It's like this. Here you go. It's like this. Technically there's a stability point right here. Right there. Right there. Right there. Okay? But if it's a little bit off, it starts to fall, right? Oops.
Yeah.
A little bit. It really falls. So if it's a little bit off, it starts to fall. So technically there's a stability point there, but
There's no way to get it.
you have to be exactly there, right, for it to stay. So, all right. It's much easier to get to this stability point, right? Because if you displace it one way or the other, it moves back towards equilibrium, right? Okay?
Consider mass.
So, here the forces push it back, here the forces push it away from equilibrium. So this is an unstable equilibrium, this is a stable equilibrium, and what if we had a spot like this, flat? Is that equilibrium?
Yes.
But it's neutral equilibrium,
Yes.
where you can take the object and you can move it one place or another and it'll stay. Like the floor is a neutral equilibrium position. You can take something and place them anywhere on the floor and it should stay. Right? Alright. So, if you have potential energy function here, you know the exact amount of energy everywhere on here. So, what if I started right here? Describe the motion.
It will stay.
It'll stay. If I give it a little bit of energy to start, then it will move down here, speed up, slow down, and keep going. It won't stop here, will it? As long as there's no friction, right? Okay, everybody. Oh, Andy, did I answer your question, Andy? not sure?
I think she forgot her question.
Okay, go to the second to the last problem in your review packet. In your extra, extra thick review packet. Problem 872. Okay, it says, the above graph, actually it's to the right, shows the potential energy Ux, use of x, for a particle as a function of position x. Identify all the equilibrium positions. Okay, where are the equilibrium positions? 2 and 5 meters. There you go. Bingo. 2 points. Suppose the particle has a constant total energy of 4 joules, as shown by the dashed line. Determine the kinetic energy of the particle when it's at 2 and when it's at 4 meters. All right. All right, looks something like this. All right, look. It says the object has a total energy. Energy equals 4 joules. It says, what's its kinetic energy when you're here? When you're right there, how much potential energy do you have?
1.
So if this is your total energy and your potential energy equals 1 joule, how much kinetic energy do you have? 3 joules.
Simple.
There you go. All right, so how much energy do you have when you're at 4 meters?
1.
Okay, at 4 meters, you're up here, and you're at 3 joules of potential, so you'll be at 1 joule of kinetic. All right? Can the particle reach the position 0.5 meters?
No.
Why not?
Because you're in imaginary physics.
Because in order to reach this spot up here, how much energy does it have to have?
More potential energy.
Looks like about 6 joules on our real graph, right?
Yeah.
And does it have 6 joules of energy?
No.
No, so it can't reach that. Can it reach the location of 5 meters, which is right here?
Unless it converts some of its mass into energy.
Well, it can reach it and then go through it.
Okay, so here's my question. Can it reach this? The answer is yes, because it has enough energy to reach that. Now, what if we had this? What if the object started right here? If it starts right here, what will it be doing?
Fine.
Starting at...
Right for a second, it'll be fine.
Well, it's losing.
At a decelerating rate.
Wait a minute. Tell me, at this instant, what is the motion of the object like?
It's not. It's not.
It's not moving. Why not?
It has
0.
Because it has all potential energy, 4 joules of potential.
0.
Now, describe its motion. What will it do?
Start moving.
It will speed up to a maximum. Then it will slow down to a minimum. But will it stop?
No.
What will it do?
It'll keep going.
It'll keep going. Will it ever return?
No.
Not that we know of. What energy would it have to start with in order to return? Somewhere in here, right? If it started here, then it would go like this, and it would go like this, and it would oscillate back and forth, right? Okay? All right, part E. Will you please graph what the force looks like? What is that conservative force?
Wait, so how do we phrase D?
Your answer to D is, will it reach that point? And your answer is yes, because the potential energy there is less than 4, and it has a total energy of 4, so it can reach that spot. What's the slope right here?
Negative.
Okay, it's -4. What's the slope right here?
Positive.
+1. What's the slope right here? -2. All right, so when we do our graph, force versus x, okay, the force is the negative derivative, right? So I start off at 4, I go to -1, and then I end back up at +2. So it should look something like this. And there should be smooth transitions in between. And that's it. Now, if we give you any other kind of strange function, like this, say my potential energy is x, no, let's do x plus 3 cubed minus x squared plus 14x plus 6. And I ask you, what's the force? The force is the negative derivative of that. Okay? All you do is take the derivative, make it all negative. And that's the force function for that potential energy field or function. Okay? Now, what's really cool about this is that if you have these conservative forces, like I said, you have all these different planets. All you do is overlap all of their force functions, take the integral of them, find the integral f dot ds of all of them, and that's the negative of your potential energy function. So you can graph out the potential energy and see where things will want to fall into. Okay? What's really cool about that is you can do that for charges, and you'll end up with, if you have plus charges and minus charges, you'll end up with a potential energy function for this that will look like this. You'll have one of these things where you have positive energy close to this, negative potential energy close to this, and you can see where things will fall towards, which is really kind of cool. And you'll know exactly how fast they'll be going when they get there. It's all potential energy. Potential turns into kinetic. Really cool. All right, how are we doing? Questions?
Good, well.
All right, since you're doing so well, here's what I want you to do, is go to the first free response problem, and solve this one. What we're going to do is we're going to take some practice at some work energy problems, and then we have one last thing to add. We've already added potential energy functions and how to handle them. That's our first new thing. Our second new thing is going to be rotational kinetic energy. So we're going to add rotational kinetic energy on Tuesday. And then that'll be it. And we'll have a test.
Hooray.